Good afternoon, my dear student. I am Dr. Biswajit Gayan, Assistant Professor, Department of Chemistry, your college, Dr. Sudhit Chandrasood, Institute of Technology and Sports Complex. Student, in my previous class, I have discussed about the water chemistry. So, you know that the water is universal solvent. So when water we consider the water to the question of the water, then the question of the solubility will become, or basically the solution. So today we will discuss about the solubility product and some basic concept of acid, base and salt. So acid, base, salt and solubility product. So from the beginning, or from the 10th class, 12th class, 12th level, you have already have some idea about the very simply the acid or the species or the substance which produce H plus, and the aqueous solution is called acid, and for base or alkali which produce OH minus in the solution. So these are very well known. And salt is basically when an acid and base are reacted, then two things are formed. One is salt, another is the water. So we can define that when acid base reaction, the product form other than water is called salt. So salt is basically um, is form of for a cation and anion, which is called the cation is called acid, cation is called basic radical, and anion is called the acid radical. So okay, I am not going to details about this thing, but I want to start from the thing about the common ion effect, that is the ionization problem. So if I think uh, acid, particularly acid, so two type of the acid is possible. One is the strong acid, another is the weak acid. So if we consider the strong acid means in aqueous solution it is completely dissociated, and weak acid means, yes, this type of the acid will be not completely dissociated. That's why the number of the H plus in the solution will be low, and that's why it is weak acid. So very simply, strong acid means it is completely dissociated or higher extent of the dissociation of the compound, and weak acid there will be a degree of dissociation, not completely dissociated. So in this concern, HCl, sulfuric acid, HNO3, these are the strong acid. But acetic acid, formic acid, and other like fumaric acid, citric acid, these all are the weak acid, because this type of the compound in the aqueous solution is not completely dissociated, but a percentage of this acid will be dissociated and form H plus. So what do you mean by common ion? So if in your solution there's more than one material, and if the produced cation or anion in the solution is common, then there will be a disturbance of the dissociation of the weak material will be happen. So again I want to summarize the thing, please note it. So when two species are present in the aqueous solution, and if after dissociation it produces a common matter, that is a common cation or common anion, then if the species, if any species is weak, then the dissociation is hampered by due to this common ion effect. And this is basically the application of the Lasatier principle, though it is Lasatier principle is not chemically applicable, but yes, we can say yes, it is a concept of the Lasatier principle. If your right hand side the product, the concentration of the product will be high, then the dissociation of the reactant will be low. So here the simple example of the common ion effect is the very common example is the mixture of the sodium acetate and acetic acid. We have already known that acetic acid is a weak acid. Now the sodium acetate, that is CH3COONA, here sodium acetate is a strong electrolyte. It is basically salt. So it is completely dissociated in the water, and 100% it produces Na plus and acetate anion. Now in the right hand side acetate anion is present. Now when acetic acid will be dissociated, it produces one H plus and one acetate ion. As in the solution there is a number of the acetate ion present from the dissociation of the sodium acetate. So the dissociation of the acetic acid will be decreases, or by amount of the addition of the sodium acetate we can control the dissociation of the acetic acid. So this is called the common ion effect. Now so this type of the thing with the salt and weak acid is form actually buffer solution, and for this the pH will be not simply by the concentration of the H plus ion only, but here the concentration of the salt play an important role. So here for the salt of weak acid and strong or the salt Na, so in that case it form the Henderson equation will be applicable. So Henderson equation for the buffer solution is like this: pH equal to pKa plus log the concentration of the conjugate base by acid. So basically this is the conjugate base, means here the acetate anion, if we consider the previous example. So there will be pH is not directly the concentration of the H plus. So here the pH is equal to pKa, that is the pKa means minus log of Ka, that is dissociation constant of the acid, then log conjugate base by acid, that is the concentration of the acetate minus and acetic acid by acetic acid. So ultimately we'll get the pH value, that is pH is equal to pKa plus log concentration of the A minus by concentration of the H minus. In generally we consider the concentration of the salt, because if the conjugate acid is present, if the salt is present, so it is completely dissociated. So this is the concentration of the salt. So we can replace the concentration of the conjugate base by salt for our purpose. Now this is the problem. So what will be the pH of the solution containing this molar of acetic acid and this molar of the acetate salt, potassium salt actually. So here if you look into the equation, so pH plus pKa plus log this. So here the pKa value for the acetic acid is 3.77. So we put I put 3.77. Then we consider the concentration of the sodium acetate is equal to, sorry, potassium acetate is 0.52 molar, and then 0.30 is the concentration of the acetic acid. So then we'll get the pH of this solution, this is actually buffer solution, is 4.01. Clear? So there will be this type of the problem, and now we will be elaborately discussing about the buffer solution. So buffer solution is a solution which resists the change of the pH after the addition of a small amount of acid and base. If you suppose there is a solution, and if you add some amount of the acid, the pH will be not change. But if you, yes, if you add a huge amount of the acid, then obviously it will be changed. But in case of the buffer solution, so it try to keep the pH fixed. So like in our blood, like in our saliva. So basically in blood the pH is fixed, because if the pH will be changed, then there will be a problem and lots of problem in our stomach. If it's a change, then there will be lots of problem in digestion, and that is in lots of enzymatic activity pH is fixed. So in that case the buffer medium is required. So uh, our blood is basically an example of a pH solution, because it maintains the pH by phosphate ion. Now very simply, a buffer materially can be defined that it is a combination of the weak acid and its salt, and if we consider a weak base, then its salt. So weak acid and its salt, weak base and its salt. So if we take the example, that is acetic acid and sodium acetate, yes, this is the example. So strong So now we are considering a buffer solution and a normal water. So here you look here for the sodium acetate and the acetic acid buffer. So if you add here in this solution, in the buffer solution, that is HCl solution is added, then the pH will not be changed. The pH will be remain fixed at below 5 and above 4. But if we add HCl in simple water, then pH will be decreases. So there will be sharp decrease of the pH. But in case of the buffer, there will be no change of the pH. This is the beauty of a buffer solution. It keeps the pH of overall solution at a fixed value. So these are the thing, the following a buffer system, that is KF, HF, KBr, HBr. KBr is a salt, HBr is a acid. This type of the thing is happening, and lots of example. Please go through the book and other system, so then you can get the lots of example of the buffer solution. So here in the another example, that is the example of the ammonium solution, that is ammonium hydroxide and NH4Cl. So this is a basic buffer. So this is a very commonly used in number of titration purpose. So NH4OH, NH4Cl is a buffer solution, and if I say acidic buffer, then CH3 CH3COOH, that is acetic acid, and CH3COONA, that is sodium acetate. This is the combination of acidic buffer and basic buffer. So chemistry in action, yes, this is plasma and plasma. So here the pH is fixed. So if I if I say you about the titration, yes, it is very well known for you, because titration, you know that the acid base titration. So in the titration is the basically procedure where a unknown um, acid solution or the basic solution is titrated by the base or acid. So equivalence point is the point at which reaction is completed. So because so it is a one type called, it's a neutralization point. So neutralization point when the acidic solution is neutralized by alkaline solution, and at that stage the pH is nearly about 7, but not exactly 7. So it is very close to the 7 but not exactly 7. Please remember it and try to note it. So equivalence point means not means that it is pH 7, but it is nearly about 7. Equivalent point, the point at which the reaction is completed. Yes, I have already told that the H plus and OH minus form H2O. So this type of the reaction will be completed. Indicator is a substance that changes the color at the equivalence point. So it helps to detect the equivalent point. So there was suppose a titration like acid and base, and both are strong. So suppose we are titrating a acid solution, unknown acid solution, by a base, that is NaOH. So first we take the acid solution in a beaker, then fill the burette with the NaOH, then we add NaOH solution dropwise. So if you look that at the curve, then the pH will be changes, but initially the pH will be not changes very fast, but at at nearly about the equivalent point there will be a huge jump from pH 2 to pH 11. Why this type of the jump is happening? Because if you consider this reaction, so here OH and H plus form H2O. Now suppose in your solution you are taking acidic solution, so in your solution mainly H plus is present, no question of OH minus. Now you are adding OH minus, so it will be form water. Again you add another OH, then another OH, then another OH, so then it will form water. So it will be the H plus will be decreases. Suppose if we consider that the 100 number of the H plus is present, and if you are adding 1 OH minus, so suppose at the point that is at the 95 drop 95 OHs you have added in that during the titration, so there will be a presence of the 5 H plus. So yes, if it is a 5H plus, it show its acidity, because yes, it is a 5H plus is present, but there will be very few amount of the H plus, so it will become closer to the 7. Now when you add extra 5 drop, or sorry extra 5 H plus, then it will be neutralized, but we will not observe that value because there will be maybe some difficulties or we can miss it. But after adding 1 2 3 4 5 number of the OH minus, or one drop of the OH minus, that is in a solution, then the pH changes to the acidic to the basic. So basically acidic pH is below 7 and basic pH is above 7. So in that case a sharp change will be observed. So if H plus is present, its pH will be below 7, and if OH is present in extra, then the pH will be the basic region. So there will be sharp change is observed like this curve. So this sharp change is basically the equivalent to the equivalence point. So this is a very simple thing. and this is actually followed by the titration, and there will be lots of different kind of titration and their nature are different, but ultimately the concept of the equivalence point is same. And so by this, using this concept of titration, one can standardize the unknown acid or unknown basic solution. So this is the actually a natural indicator, that is the solution obtained from the cabbage, and if you keep it in the defined pH value, their color will be defined. It's like this. So at lower pH the color is red, and in the higher pH it is yellow. Another one thing I want to discuss, that is solubility product. So for sparingly soluble salt, what do you mean by sparingly soluble salt? Means it is not completely soluble but somewhat soluble in the water. So AgCl is that type of the example. So if you put AgCl in the water solution, then it will form an amount of the Ag plus and Cl minus. So it is in equilibrium, that is AgCl and Ag plus and Cl minus. Now that is Ksp is the solubility product, that is in that equilibrium. If it is a no precipitate, no completely solution, it is that is under the equilibrium, then the Ksp is the product of the Ag plus and Cl minus, and it is the standard value, because in equilibrium for saturated solution, yes, the value is the Ksp. So the solubility at equilibrium or for saturated solution, and their product of cation and anion is basically the solubility product, and it is denoted by Sp. So solubility product, the constant, it's basically, and it is constant for a particular temperature. So if we consider the AgCl, AgCl, it is Ag plus and Cl minus. For AMF2 it is Ksp equal to concentration of the magnesium and concentration of the fluoride and its square. So, and another thing, that is ionic product. What is the ionic product? Ionic product is basically the multiplication of the cation concentration and anion concentration. There is no question of the solubility product. So ionic product is different than solubility product. So solubility product is applicable when it is the pure, but ionic product, suppose we add AgCl, now we add AgNO3. So here, yes, AgCl actually produce some Ag plus, and from the AgNO3 it also produce some Ag plus. So here the concentration of the Ag plus will be increases. So this at that time the product of the Ag plus and the Cl minus will be defined. So in very simple cases, if the ionic product is less than Ksp value, that is solubility product, then it will be make a solution. There is no question of the precipitation. But if it is the equilibrium, then it is called solubility product or saturated solution. And if the ionic product is greater than Ksp or the solubility product, then there will be precipitation of that salt. Very simple. So there will be lots of salt and their Ksp value. So if I go to the example, and this solubility and the solubility product can be expressed in gram per liter, and molar solubility is expressed in the mole per liter. So here if you look the next example, suppose we are looking for this example. So here we are considering the KCl2 and NaOH. So when we add NaOH to the KCl2 solution, then at a particular time it will be precipitated. So here the concentration of the potassium ion is 0.1 molar, and the concentration of the OH minus is 4.0. Here again, please try to understand. Here it is here the concentration of the OH is 4.0 into 10 to the power minus 4 mole. That is a concentration expressed in the molality, because you don't misguided with this thing, that is 0.2 molar NaOH, but it is added 2 ml at 0.2 molar NaOH in 1 liter solution. So ultimately the concentration of the OH minus decreases. So ultimately it is in molarity it is 4.0 into 10 to the power minus 4 molar. So now the ionic product is basically 0.1 into 4.0 into 10 to the power minus 4 to the power whole square in case of the calcium hydroxide, because calcium is 1 but OH is 2, so it will be go to the square. So ultimately it will be 1.6 into 10 to the power minus 8. So this is the ionic product, but the Ksp value of the calcium hydroxide is 8.0 into 10 to the power minus 6. So if we look to the Ksp value and the ionic product, we will see that the ionic product is less than the Ksp value. So if you add 2 ml 0.2 molar NaOH to 1 liter of 0.1 molar calcium chloride solution, it will be not precipitate. Clear? Because the Ksp value is greater than ionic product. So here is another example, that is just opposite, that is solubility. So in case of the normal AgVr, the solubility is 8 point, that is Ksp is a square, that is solubility square, that solubility is 8.8 into 10 to the power minus 7. But if the NaBr is present, then it produces a higher number of the Br minus. So when AgBr come to the solution, their tendency of the formation of the Br minus will be decreases. So here the concentration of the bromide, that is solubility of the Ag plus, that is AgBr will be not dissociated, but inversely it will be Ag plus and Br minus will be combined and form AgBr. So in that case solubility will be 7.7 into 10 to the power minus 10. So here in the left hand side the solubility of the AgBr is 8, yes, solubility is 8.8 into 10 to the power minus 7, but here the solubility of the silver is 7.7 into 10 to the power minus 10. It is very low, because here due to the presence of the bromide from the sodium bromide, the solubility of the silver is decreases, and this is the solubility of the silver, that is 7.7 into 10 to the power minus 10. So we can control the concentration of any ion, cation or anion, by some other salt or acid or defined electrolyte. So this is the beauty of the solubility product, and solubility product is the base of the group separation. That is, we can separate the metal ion present in the solution one by one, but stepwise. So this is by using the solubility product and using the different solution we can precipitate the defined metal ion at the defined group very specifically. So I hope that you understand the acid base and its salt, and ultimately the solubility product and the application of the solubility product. So thank you student for your kind attention. And if you face any kind of the problem to understand this or any mathematical problem, please inform me, and I will obviously try to help you, and I will help you with my best. Thank you.